Hi everyone, I'm Aditi Pandit. I'm an engineer at Ahana IBM, and I'm going to talk today about TPC-DS benchmarking using the Presto native engine. So this is the first of two talks today from IBM on TPC-DS benchmarking. This talk is focused on the native engine in open source, and we're going to compare it with the Presto Java engine as a baseline. Uh, the next talk is about taking the native engine and putting it in watsonx data. So that has a new query optimizer as well. The runs in this talk use the Presto query optimizer in open source. So in this talk, we'll start with an introduction to TPC-DS and give a high-level overview of the benchmark. Then we'll drill down into an analysis of the TPC-DS power runs at different scale factors. So we have runs of 1K, 10K, and 100K. We'll cover the main performance enhancements that led to the numbers, a bit of future plans. And also these benchmarks were run using the pbench tool that has been open sourced by our team as well. And Ethan will talk about the pbench tool at the end. So the TPC-DS benchmark is a representative evaluation of a decision support system. So this can be like a data warehouse, a lake house, and it uses the model of an enterprise in the retail space to actually model a realistic phases. So that's both the data loading and the query that data infrastructure needs to support for DSS. This is a fairly complex benchmark and really showcases capabilities of the system. It's become pretty hot in recent years, and many data platform vendors are using it to demonstrate their capabilities. So the TPC-DS benchmark assumes that all the benchmarking, the reporting and analytic queries are being done on a data warehouse. This is separate from the systems that run the operations. So your actual real-time transactions are happening in an operational system. The reporting is in the data warehouse. There is a periodic refresh process that kind of updates the warehouse with the operational data. And the benchmark models this as well. So the steps of the benchmark are, it starts with a load test where the data, the benchmark comes with the DSDGen program, and you can use it to generate data at different scale factors. So the first step is to generate this data, host it somewhere, and load that data into the warehouse. The database load is followed by the query runs. There are two variations of the query runs, a power test and a throughput test. So the power test is a serial run of all the queries, and the throughput test is multiple concurrent serial runs happening at the same time. So the TPC-DS benchmark doesn't prescribe a certain set of user sessions, but there is a minimum threshold on how many user sessions should be run concurrently. So post the query runs is a data maintenance phase where the warehouse is updated with data from the operational store. So once again, the DSDGen program can be used to generate these Delta files, which comprise deletes and inserts of new records into the tables. This data maintenance phase is followed by another query run phase. So again, a barn throughput run. And this comprises all the steps of the benchmark. So the TPC-DS benchmark also prescribes what is the performance metric. And this is the number that's used to compare the different systems. So this formula is for something called QPH, and that's like query per hour. So the metric is actually the number of queries run at different scale factors, and that is kind of divided by some normalized time of all the runs, the elapsed times of all the phases. So it's like the power run, the throughput run, the data maintenance, and the load phase. So the higher the number of QPH, the better the system is. In terms of the actual TPC-DS schema and queries, so the TPC-DS schema uses the model of a retail business inventory for the queries. So there are three components So the three different dimensions of tables. So there's the store sales and store returns, the web sales and web returns, catalog sales and catalog returns. So these are the six main fact tables in the schema, and these can be joined with multiple dimensions. So dimensions are a snowflake style schema of like three main entities. There's customer, items, and a time entity. So as you can see, the customer tables are a snowflake with customer address, demographics as well. And so you have these three these three style of fact tables being joined with all the dimensions for the queries. The TPC-DS queries, there are 99 queries, and they can be classified as reporting, ad hoc, iterative, and data mining queries. So the reporting queries are used to generate reports about the financial and operational health of the business. These are fixed queries that repeat at a regular frequency. The ad hoc queries are for immediate answers to business questions. And both sets of queries can be run in the same benchmark because the benchmark allows you to generate auxiliary structures only for the tables in the reporting queries, not for the ad hoc queries. Um, there are also like iterative style queries where the results of the first query are used for the next query to allow for exploration of business data to discover new insights. And the data mining queries typically sift through huge amounts of data and return a large number of rows. So in terms of what we have done with this TPC-DS benchmark, a lot of the work in the previous year was to actually get to the feature completion for the TPC-DS queries. So the TPC-DS queries are fairly complex. They involve analytic functions, window queries, roll-ups, use the decimal data type. And so there was a lot of work to get to the place where these queries can run. We verified results for 1K and 10K. And the most of this year has been focused on doing the power runs for one terabyte, 10 terabyte, and 100 terabytes. So going to the power runs, this graph shows the results of running the TPC-DS 1K run using the Presto OSS native and Java engines. So I've used Presto 288. I haven't given the specifics of the clusters used here. You can email me for more information. But the clusters are regular, like Amazon EC2 clusters. This is like a typical like medium-sized cluster with 8 nodes, 128 gigs of memory each. So the red line represents the native runtime, and the blue line represents the Java runtime. As you can see, there are improvements across the board, but this graph sort of gets a bit biased by the Q67, which is an outlier. And so we've also plotted a graph of the duration ratios, which is the Java runtime to the native runtime. As we can see here, there are improvements across the board, and several queries show an improvement of 10x. So the main points up to here were that like this is like the ideal setup for Prestismo and vlogs. The queries kind of sort of fit in memory. The runtime is of the order of 1 or 2 minutes with just Q67 as an outlier. And the main challenge was getting the functionality and correctness to this point. The emphasis in this run is mainly on optimizing the CPU times for the operators. And so there are multiple optimizations that were added to the most time-consuming operators, and hash join especially sort of stood out. We have a few optimizations for duplicate rows, for joins with duplicate rows, for semi and anti-join cases. I have a list of the issues and PRs in a later slide. From there, we went to the 10 terabyte run, and the 10 terabyte run is on a little larger cluster of 16 nodes with 256 gig memory. And the native finished in 2.19 hours, and the Java took 3.8 hours. So this is like close to double the runtime. And as we can see here, many queries improved as well. In terms of the duration ratios, um, we see many improvements across the board here as well. So in this run, what sort of came up is that we begin to constrain the memory use of the system, right? So like the data is 10 terabyte in size, and we had only 4 terabytes in the actual cluster. So we kind of began to see a lot of improvements because of async data cache, split prefetching. But using async data cache also came with certain issues. So the async data cache, right, it tends to grow up to the system memory. And in our runs, we had sort of kept the system memory very close to the node memory. What we began to notice is that there were places of unaccounted memory usage from external libraries, especially like we did these runs with Parquet, and also the Proxygen library used by HTTP. Kind of had some memory allocations that were not counted by the vlog system. And so that would lead to several situations. So of course, the one obvious thing to do is to leave more headway for these allocations. But in order to actually enhance the efficiency of the system, a new infrastructure called the periodic memory checker was added. And this monitors the system memory and allows you to trigger a shrink of the async data cache when required. From here, we went to the 100 terabyte run. Now, this run is on a fairly high-end cluster with 64 nodes and like high-end machines with 512 gigabytes each. So I haven't done a Java run because it's prohibitively expensive, but the native engine with just the Presto optimizer kind of completed this run in under 4 hours, which is super impressive. At this point, what we began to observe is that the exchange became a bottleneck in this run. Meta kind of noticed that in their internal traffic as well. And at this point, a full redesign of the exchange protocol was proposed. Um, to describe at a very high level what the change was, is that the original protocol kind of sort of went in a round robin way across all the nodes in the cluster at fixed intervals. But the new protocol is sort of greedy in its approach and goes to the nodes that have generated the most data first. So this really improves the system throughput. There were also other fixes that were related to the spill bits of the join, where the data is read back in the hash table post spilling that helped here. So to summarize all these improvements, I've listed out the main issues and PRs that kind of track more details of the specific situations that happen. So the redesign of the exchange protocol, the periodic shrink, all the hash join optimizations are kind of listed here. So what do we intend to follow through with? For H2, we are planning to focus on the throughput runs. So this will be multiple concurrent user streams. So given that, this will put high pressure on the spilling and memory arbitration code paths. So it'll be interesting to see like what gets unraveled next. We are working on fixes for all the memory accounting inconsistencies. The exchange part of the system tends to be is also like still highlighted, and we have kind of noticed some locking improvements in the partition output that could help in the multiple concurrent case. Presto 0.288 also has the common table expressions. Common table expressions are widely used in multiple queries in TPC-DS benchmark. So we're kind of excited to see like the improvements that this would bring. And there are a bunch of improvements in the Parquet reader that are being proposed as well. So here I will hand it over to Ethan to talk about the pbench tool that we kind of used for the benchmarking.
Hi everyone. I'm going to talk about the pbench tool. So this is a tool basically we built from scratch from this year in IBM to replace Benchto. We kind of built in a lot of capabilities we need for benchmarking into this tool so that it can support the query groups in a very flexible way, and you can define dependencies with them among them. So you can also do the concurrent query workloads. It's something that we don't have a good support in Benchto today, and it's also required for the throughput test phase in the TPC-DS. So also, we want, through this tool, we want not only be able to run the benchmark, we want to understand the performance characteristics when we run the queries, and so that we can dive into the details and identify optimization opportunities. So while we run the benchmark, we built in some capabilities to collect the query logs and also collect the query results in case we want to verify the correctness of the benchmark queries. We also added the randomized execution support so that we can have a pool of queries that keep running that we randomly pick queries to run. And we also built in a capability of generating a cluster configuration using templates. Because when we test the Presto Java and Presto Simo, there are actually a lot of the configurations and we need to tune. Especially there are plenty of memory-related knobs that we need to tune. And those values actually scales with the cluster size and the configuration. So in order for us to have a way to precisely determine those values, we introduce this so that we can compute and populate the cluster configuration based on a specified formula. So not only we want to do this benchmark run, in this tool, we also built in some additional capabilities to do table stats save, query log replay, and traffic mirroring. This is more from the need to running some customer-related workloads. Because when we do the lakehouse offering, benchmarks like TPC-DS only represents, like, I would say, 5 to 10% of the day-to-day workloads our customer would run. So in order to further stress test our system and finding issues proactively, in addition to TPC-H, TPC-DS, and those standard benchmarks, we want to be able to model some workloads that closely mimics our customers' production workload. So we are doing some synthesized data and also trying to replay some of the customer workload in our test environment. So those capabilities are built in there to extend the capability of pbench so that we can do both standard benchmarking and also workload stress tests from the customer. So the source code of pbench is now pushed to open source. So you can check it out, this pbench repo under PrestoDB. And we also added a very detailed documentation on those knobs and how to use the tools and how we use it so that you can easily get started with the documentation on GitHub. Can we move to the next slide? All right. So with pbench, we were able to set up an infrastructure that actually have very detailed monitoring of all the test clusters we have. So we collect the query logs, we collect the time series metrics, and also the Docker container stats, so that when we have a benchmark run, we'll be able to have like a 360 degrees of observations on the environment and the engine and the query statistics. Next slide. So the next slides are some screenshots of our current dashboard. It's also built around pbench. So this is our benchmark run view that whenever a developer starts a benchmark run, a row will show up here for them to pick and compare. Next slide. By the way, Aditi, can you turn on the full screen, the presenter view? This is in your, yeah. So this one, once we click into a benchmark run, so this view will list all the queries included and all the time measurements. And also you can select multiple runs to compare. And when we drill down to each query, it will show all the query for this particular run. And then the query ID so that we can hop onto the breakdown analysis. Next one. This is comparing the run. You have the speed up comparison. That's the graph that Didi just showed in her slide. Next one. And for individual query we select, we were able to, because we collect very detailed query stats, and we are able to visualize like the query plans and all the operator level stats, etc. Next one. And also, when we select multiple queries, we have built-in tools in Grafana just to do the plan diff, so you can tell the differences in the query plans. This is especially useful when doing detailed like drill down performance analysis. Next one. Also, thanks to Ying and other developers on our team, we have a lot more detailed dashboard, like with the pie charts on each operators. It's also helpful when we determine what operators are lacking. Yep. Go ahead. Yeah, also because we collect the time series stats for things like memory and CPU usage, and also cache hit, etc. Those metrics, we are able to get a real-time analysis. And in Grafana, they're also interconnected. So we're able to click on a query, and that takes us to a view that just show the cluster status during the time window when the query was run, and also all the containers within the cluster at that time. Yeah, next one. And also for each container, this is especially helpful when a cluster ran into some issues, like some worker pod crashed. Then we're able to persist all the logs, and all of them are accessible within Grafana. Yeah, I think that's the end of this one. Yeah. All right. Yeah, we can take any questions if someone have any questions. All right. So I think we can conclude the session. Ready?
Yeah, I think so.
Yeah. Okay. Thanks, everyone.
Everyone.
Mm.